Yes. Okay. So in model analysis, this is very much important. This is actually a part of the vibrational analysis, where for every material, a structure made of a particular material, it is going to have a particular uh, model frequencies. That is nothing but resonant frequencies at which, when it reaches this particular frequency, the vibration of this material is going to be very high. It is going to be up to, nearing the infinity range. Okay, so only small frequency range. Okay, at that particular time, what is going to happen is its vibration will be too large, where we cannot control it. So one example for this is that, say for example, when we go in a two-wheeler. Okay, when we go in a two-wheeler, uh, especially when it is a splendor bike and so on, every vehicle in case. Okay, when you go in the when you take up the example of a splendor bike, when you go from the range of say for example 50 to 55, okay, you can see that the entire vehicle is going to vibrate. So until that, the vehicle is going to run smoothly, but after that particular, when you reach that particular range, the vehicle is going to vibrate. Okay, so this is because it is somewhere nearing its resonant frequency, right? So that is why, without doing anything, just going at that particular speed, okay, that means inputting so much of force, it is reaching its resonant frequency. And what is going to happen is, you can see you can feel the vibration. So the next thing is that, you would have seen this particular thing. Just a second, I'll just share it to you. Yes, this particular bridge, okay, wire bridge, okay, in the 1940s when it was being constructed, right, it was collapsed totally just because of wind force. Okay, we very well know that the wind forces are not so much, but the entire thing just got collapsed just because of the wind, the heavy wind that was blown. So what happened over here is that, so once this wind was blown over here, over these bridges, okay, this bridge started to vibrate, okay, to randomly move in different positions. So at but that particular one particular frequency, okay, what is going to happen is that it has been very much nearer to the resonant frequency, so that it no longer, it started to vibrate so severely, so that it was totally collapsed. Okay, no heavy loads were actually applied. It was only the wind force that actually took place. So like this, so this bridge had a particular resonant frequencies, which is called as the modal frequencies. Okay, so just because of that, once it attains over there, okay, it is going to collapse. So for every system, we have to determine what is the model frequencies for every structure, right? Okay, so yes, now let's see how to do model analysis using ANSYS. Okay, so let's take up a simple problem. Okay, yes, okay, okay, yes. So let's see how to do it step by step. Okay, okay, so this is the problem, right? Uh, so we have a a cantilever beam, okay, having a cross section 10 mm by 15 mm, right? And 2 e power 5, that's nothing but for the steel, Poisson's ratio 0.3, density of steel that we are going to take. So 0.00785 grams per millimeter cube. So we have kept everything in terms of load, in terms of Newton, length measurements, scaling measurements in terms of mm, right? Okay, so the length of the the length of the cantilever beam is 1000 mm. So now let's see how to do the model analysis for this. So we'll go to ANSYS, right? We'll go to ANSYS, right? So first thing is the preferences, okay, structural, Okay, it's a structural type of problem. Preprocessor, it's a beam type of problem. So element type will take beam and node 188, two node 188. Okay, right? So that is going to be the element type because it's a beam. It's a beam type of structural member. So next, we are not going to give any real constant, that is the cross-sectional area and so on. Okay, we are going to give is about the uh, material properties. Okay, right? So material property linear, elastic, isotropic. So 2 e power 5 and Poisson's ratio 0.3. Then similarly go just below that after non-linear, the next option is we have density. So we'll input the density over here. Okay, and yes, that's all over here. Next, now we have given the material properties. We have to give the cross-sectional area and so on. So it's a beam. So we'll go to sections. Okay, beams, common sections. It was actually a rectangular cross section that we had seen, right? So in this particular window over here, okay, we shall give the cross-sectional member. Usually it will be in the rectangular cross-section itself, that is over here, width and height. So width is 15 mm, height is 10 mm, and click on OK, right? Next, now the moment we give uh, the cross section of the beam, okay, over here, the moment we fill it over here, it is going to take up the other values, that is the centroid, IZZ value and so on things, okay, right? All those is going to be calculated automatically. So now let's go to modeling. So we'll use it using key points in active CS. So first key point at 0, 0, 0. Second key point, the length of the beam is 1000 mm. So we'll input that for key point number 2, 1000 mm. So we have 0, 0, 0 and key point number 2 at 1000 mm. So yes, connected by straight line. Okay. Yes. Next thing is that we have to, before meshing it, we have to break it into smaller pieces. So we'll go to mesh tool. Okay, meshing, and then we'll go here for the element size. Okay, we'll make it into smaller elements. 10 or 100 should be the length of each. So we are going to give only 10 mm should be there. So the overall length is 1000. So we'll have 100 such pieces over here. Then go to mesh in the same main option. Okay, then mesh all these small lines that was created. Right. Now go to the analysis type in the solution. New analysis, this is the change that we have over here when compared to our normal structural problem, right? Okay. Okay. Yes. So here, okay. So here we have different options. So here what we can do is we have to go for model analysis. Right. Okay. Then yes, how many mode shapes do we want? That is for how many resonant frequencies do we need? Okay, that we have to input that particular detail over here. Okay, and yes, what is the starting and ending frequency range? Okay, we don't need to give that because there is no load applied over here. Okay, yes, it may be in any range. We have only given 6 resonant frequencies. We don't know what is the sixth resonant frequency, whether it can be 1,000 or it can be even 2,000 or anything like that. Okay, we don't know that. Right, so we'll continue here. So as usual, it's a simply supported, cantilever beam. So one end of it is fixed. Okay. Now go to solve. No need of applying any load over here. Solution is going to be done. It's going to do all the solution required using the model analysis calculation methods. Then go to general processor. Okay. In read results, we can get we can get the all the details. So if you look at this, okay, so what is the first resonant frequency? So the first resonant frequency over here is about 8.153 into 10 to the power of minus 3. Okay, this is the first frequency, resonant frequency, that this particular material or structural member is going to have, right? Okay. Then second at 1.22 and slowly it increases, and fifth one we have it at 0.14 and then at 0.21 hertz. Okay, right. So for each one of them, how the structural member is going to vary, we will see that. Okay, so these are the six sets of uh, resonant or model frequencies that is obtained for this particular structural member. Now we'll see how the shape of this is going to be there. So after the read results, we can take one set, or it's indicated by load step 1, right? Sub step 2, 3, 4, and so on. Okay, right? So first step, second, third, 5, 6, 4, and so on. Right, so we'll select the first one. We'll see how it is going to deform for this particular frequency. So take that is, we just ask it to read for that particular value, then go for plot results. Okay, deformed plot. Here we can choose our option, whether it's only we want to see only the deformed shape or deformed plus undeformed also, right? Okay, so we select deformed plus undeformed also. So here I just draw it so that you can see. So the white line is actually the without any frequency at 0. Now we can see a small dark blue line which is going across like this, right? So this is going to be the gap. Okay, so it's going to first deflect like this. Okay, for the first model frequency. So for the So we can pick any one of the frequency which is there in the list. So for the third resonant frequency, we have picked. We will go to plot results once again, deformed plot, yes, and select this and OK. So now we can see over here for the third resonant frequency, it is going like this, and then like this, and compared to its neutral portion. So that's how that is going to be the shape or the deformation of this particular structural member for the third resonant frequency or model frequency. So if you look at this for the last one, it is going to be like this, like a sinusoidal wave, right? So like this, different shapes are going to be obtained, and what we need is actually the frequency as well as the uh, uh, the deformation, because based on this, what they will do is that further on, so for this particular thing, they will modify the structure at that particular places. Okay, they may arrest it by using some other support in a particular direction or in both the directions required, so that for that particular frequency, when it is being after the modification when it has been done, the the member is not going to deform like this. So the resonant frequency is going to be avoided. So in this case, so for this case, if I arrest the beam, okay, here and here, okay, then what is going to happen for this particular frequency when it is going to attain, it is no more going to deform like this because it is already arrested over here, right? So it cannot deform like this. So at that particular frequency when this member is subjected, okay, when it reaches due to some force, dynamic forces, it will not deform like this because it has been arrested. So we are going to neglect or avoid that particular resonant frequency so that the vibration at maximum range is going to be avoided so that the structural member will uh, will not fail. Okay, right? So that is why this resonant frequency is required. That is why the model analysis is going to be done for every member. Okay, right? Yes. So this is the reason why the model frequencies are actually required. So yes, now you can see that uh, the shape that is going to be for that particular frequency, how the member is going to deform gradually, right? Right? That is what has been animated over here. Okay. Yes. So yes, this is how the model frequencies will be uh, analyzed for a simple beam problem, right? Okay. Right.